Good day, this is Dr. Wiggins and I will be discussing the answers to worksheet 8. Let's have a look at question 1. In part A, we want to determine all the directions in which the following function increases at a rate of 1 at the point 1, 1. Alright, so we need a formula for the directional derivative. And the good news is we can use theorem 95. But before we can use theorem 95, we've got to make sure that the conditions are met. And so we can start by saying that since it is differentiable at the point 1, 1 by theorem 95, the directional derivative of f in the direction of u can be calculated as grad f at the point dotted with u, where u is an unit vector. All right, and we want this value to equal 1. Now, remember that grad f is a 2D vector since f is a function of two variables. The first component is f partial x, and the second component is f partial y. And looking at this function, f partial x is expression x, and f partial y is expression 2y. So grad f at the point 1, 1 is the 2D vector with components 1, 2. All right, so now we know that the directional derivative of f at the point has a value of 1. So this means that grad f dotted with u has a value of 1. Now grad f is the vector 1, 2, and u is the vector u1, u2, and that's have the value of 1. So we know that 1 times u1 plus 2 times u2 equals 1. So we have one equation and two unknowns. But remember, u is not just any vector. U is a unit vector. So that means that u1 squared plus u2 squared equals 1. And that is our second equation, since u is a unit vector. So very important, u is a unit vector. Now, I'm going to leave the algebra to you. So you've got to do the algebra. But as a hint, from equation 1, we can get that u is equal to 1 minus twice u2 and sub it into equation 2. So it's into equation 2 and solve. So if you do the mathematics, I'm sure that you agree with me that the answers are either that u is the vector 1, 0, or u is the vector minus 3 over 5, 4 over 5. So we get that there are two directions in which at that point, if you travel in those directions, that the value of the directional derivative is 1. Now for part B, it is a very similar question, but this time around, we want to know in what directions will the value of the directional derivative be? 3. Now, we know that the value of the directional derivative is bounded. So it might be to our benefit to calculate what is the maximum directional derivative of f at the point can be. Now, by theorem 98, we know that the maximum that it can be is grad f at the point 1, 1, taking the norm of that vector. So we want the norm of grad f at the point 1, 1. We worked out this is the vector 1, 2. So we are interested in the norm of this vector. So it's 1 squared plus 2 squared. That works out to be the square root of 5. Now we know that the square root of 5 is less than the square root of 9 because the square root function is an increasing function, and that's equal to 3. So by theorem 98, we see that the maximum value that the directional derivative at this point can be is root 5. But root 5 is less than 3. So what is our conclusion? Our conclusion is that there is no u such that the directional derivative of f at the point 1, 1 in the direction of u equals 3. So the answer to this question is no such direction exists. I hope you also got that. All right, now let's move on to question 2. Now question 2 again has two parts. In the first part, we want to find a normal vector to the curve given by the equation x squared times y cubed equals 1 at this time around at the point minus 1, 1. So let's start off by defining a function. So let f be the function x squared y cubed. So the curve C is when x equals f minus 1, 1, which works out to be the value 1. Now, f partial x is the expression 2xy cubed. This is continuous on R2. F partial y is the expression 3x squared y squared, and this is continuous on R2. And now, f partial x and f partial y is continuous everywhere, and grad f at the point minus 1, 1, it is the 2D vector with components f partial x at that point, f partial y at that point, which works out to be the 2D vector. When you plug in x is minus 1 and y is 1, we get the vector minus 2, 3. So by theorem 103, because all the conditions are met, we see that grad f minus 1, 1, which is the vector minus 2, 3, is a normal to curve C. Great. So now we've shown that we can use all the conditions of theorem 103 that are met. And so by theorem 103, we find a normal vector, which is the vector minus 2, 3. It is not the only answer. Any non-zero scalar of this vector is also an acceptable answer. So the answer to this question is not unique. Now let's try B. Now B is a very tricky one, and I strongly suggest that you draw what's going on here. So we have our curve C, and we have the point, a point on the curve AB. So here, we got to grab an arbitrary point on the curve. So take point AB on the curve C. That is, because it's on the curve, we know that a squared b cubed equals 1. All right, so at this point, we draw a tangent line. Let's call it line 1. And then we have a line that's perpendicular. And let's say normal of that would be the point AB, like we did in the previous question. All right, and now we can start off by saying, like a normal vector would be grad f at point AB, which would be, when in our previous expression, when we plug in x as a, we get 2ab cubed. And when we replace x with a, so we get 3a squared b squared. So this is normal to C at the point AB. So you've got to take an arbitrary point on the curve. All right. So now we consider the second line. So consider a line L2 with equation. So we got to have functions. So let's say d is 3x minus 1 minus y equals to 0. So this is our second equation, where 3x minus 1 minus y equals 0. So this is our second line. So before we can tackle this question, we need to study each line to see what is going on here. All right. And so now we can see that grad G works out to be partial x is 3 and partial y is minus 1. So this is our second line. So this is our second line, and we see no matter which point we pick, that the normal vector grad g at any point that we pick will be the vector 3 minus 1. All right, so that is the normal vector. But now we want, this is very important, we want line 1 to be perpendicular to line 2. So we want the two lines to be perpendicular. So we know that two lines are perpendicular in R2 if the product of the slopes are minus 1. But if line 1 is perpendicular to line 2, then what does it mean? It means that if we look at the direction of line 1 and we dot it with the direction of line 2, it should be 0. However, we have calculated the normals, all right? And if we calculate the normals, then we see that again, the normals should be 0. So what we end up getting is the following, that if the two lines are perpendicular, so if line 1 is perpendicular to line 2, then we want grad f at the point AB dotted with grad g equals 0. So this is the vector 2ab cubed 3a squared b squared dotted with this vector 3 minus 1 to equal 0. So what does this mean? If I dot these two vectors, I get 6ab cubed minus 3a squared b squared equals to 0. Now, note that it is not 0 and b is not 0 since a squared b cubed equals 1 because the point AB is sitting on the curve. So this means we can divide. So if we divide by 3 and if we divide by a and if we divide by b squared, we end up obtaining that 2b equals a. And this is now good news because now if a equals 2b, then we have that a becomes 2b squared times b cubed equals 1. So this in turn gives us that b to the 5 is equal to 1 over 4. And so b will be 1 over the 5th root of 4. And so a will be twice b. So a has the value that is twice b. So we've worked out that b is 1 over the 5th root of 4 and a is twice b. So a has the value of 2 over to the 5th root of 4. And so now we say that the point is that we're after here is the a value, which is 2 over the 5th root of 4, and the b value is 1 over the 5th root of 4. So this was quite a fun little question. Please go over this answer again. All right, let's move on to question 3. Now in question 3, we got to show that every plane is tangent to the cone x squared plus y squared equal to z squared. Every tangent plane passes through the origin. Now again here, there are infinitely many points on this cone. And we want to show that all of these points, we can construct a tangent plane and that tangent plane passes through the origin. So to make our lives a little bit easier, A, B, C be any point on cone with equation x squared plus y squared equal to z squared. All right, but now we want the equation of the tangent plane. And to do this, we are going to use theorem 105. But we got to make sure that the conditions are met. Now, let's rather say that the equation of the plane is, let's use g as squared plus y squared minus z squared. So the plane, sorry, so the cone has equation G equals to 0. All right. And we know that the point ABC is a point on this curve. All right. And now we can start off by saying, all right, now note that G partial X is 2X, is continuous on R3. G partial Y, that is the value 2Y, and this is continuous on R3. And G partial Z, it is minus 2Z, is continuous on R3. All right, because all of the first order partials are polynomials, and we know that polynomials are continuous everywhere. And because G is a function of 3 variables, we say that they are all continuous on R3. And now we can say, if grad G at point A, B, C, which is 2A, 2B minus 2C, is not a zero vector by theorem, and I hope you've looked at 5, we know that a tangent plane exists at that point. So a tangent plane exists at ABC. This plane has equation. So theorem 105 is quite a mouthful. Not only does it prove the existence of the tangent plane, but it also gives us the formula for the tangent plane. So the tangent plane has Cartesian equation, grad D at the point ABC, dotted with x, y, z minus the point, which is the point ABC, equal to 0. And you can see why it was important to use an arbitrary 3D vector on the cone. So we use the point ABC. And now let's do the math. Grad G is 3D vector A, 2B minus 2C. If we subtract these vectors, it becomes x minus A, y minus B, z minus C. We know that the dot product of the two vectors should be 0. And now if we dot these two vectors, we get 2ax minus 2a squared plus 2by minus 2b squared minus 2cz plus 2c squared equals 0. And if I rearrange, I get that 2ax plus 2by plus 2cz equals 2. If I take a 2 as a common factor, I left with a squared plus b squared minus c squared. Right? But now recall that ABC is on the cone. And this means something. This means that a squared plus b squared c squared, or that a squared plus b squared minus c squared equals 0. So in equation P, the right-hand side has a value of 0. So we get that 2ax plus 2by plus 2zz equals 0. This is a plane that passes through the origin. If you're not convinced, note that 2a if x is 0 plus 2b if y is 0 plus 2c if z is 0, it works out to be 0 plus 0 plus 0, which is 0. And voila, we have proved that if we take any point on the origin, which is not the origin, that a tangent plane exists, and that the equation of the tangent plane is of the form something x plus something y plus something z equals 0, which means that all of those tangent planes passes through the origin. I hope this solution makes sense. Great. So let's move on to question 4. Now question 4 was a nice, easy one, because in question 4, we get to use some of the theorems in chapter 4. Now, one of the nice theorems in chapter 4 allows us to classify the points, and that is theorem 115. So we know that 0, 2 is a critical point, and we're given some extra information. So we know what some of the second order classes. So let's classify using theorem 115. So here you've got to use theorem 115 to help you out here to classify the critical points. So let's start off with A. Now, the theorem D. So D is G double X times G double Y minus G, the mixed one, squared. So this value is minus 1, this value minus 1, minus this value, which is 6 squared. So this works out to be minus 55. And we're not so care about what the value is. We only care about the sign of the value. And now the sign of this value is negative. So we see that D at the critical point, node 2, for A has a negative value. And if you read theorem 115, that means only one thing. That means that the critical point 02 is a saddle point. That was nice and easy. Now let's have a look at D. Like calculate D. And if you calculate D, I'm going to leave it for you to do the calculation. And if you do the calculation, I got a value of 4. Now 4 is positive. Now if D is positive, then by looking at theorem 115, we need to look at more data. And the extra bit of data it is given as a value minus 1, and minus 1 is less than 0. So we know that D is positive and G double X is negative. So by theorem 115, we see that the point 02 is a local minimum. And that was nice and easy. Now let's finish off with C. So again, you need to calculate D. Now this time around, I'm going to again leave it for you to verify that if you calculate D, you get a value of 0. Now 0 is not positive, 0 is not negative. So this means that term 1 is inconclusive. So with the current data that we have, we cannot say more than that that point is a critical point. So let's phrase that. So that we cannot classify the critical point 02 without more information. So there are limitations to theorem 115. So the best we can say, it is a critical point, but from the given data at the moment, we cannot say it is a local min or a local max or a saddle point. So theorem 115 is inconclusive. So we can't say more than that. Alrighty. And now for the very last question to this worksheet, which was question 5. And we want to find and classify all the critical points of this function of two variables. So it's a nice polynomial of two variables. All right. Now you need to know what is a point when grad f equals the 0 vector. So that is the starting point. Grad f, it's a function of two variables. So the first component is f partial x, and the second component is f partial y. And so f partial x, if you do the calculation, it turns out to be 6xy minus 12x. And then f partial y turns out to be 3y squared plus 3x squared minus 12y. And now if grad f is the 0 vector, then we see that xy minus 12x equals 0, and that 3y squared plus 3x squared minus 12y equals 0. So now we have two equations and two unknowns to solve. All right. So you get really good practice in algebra when you are playing with functions of more than one variable. Now looking at 1, we can rewrite this 6x times y minus 2 equals 0. So from 1, we see that 6x times y minus 2 equals 0. So we have two options. So either x is naught or y is equal to 2. Right. So let's look at this case. So case 1, if x is equal to 0, in 2 we get the following. We get that 3y squared minus 12y equals 0. Here it is really good to factorize. So if I take out 3y, I left with y minus 4 equals 0. So we see that y is equal to 0 or y is equal to 4. And so here we get the points that x is 0, y is 0, or x is 0 and y is 4. And now let's have a look at case 2. Case 2 is if y equals 2, then in 2 we get, so now replace y with 2. So I get 12 plus 3x squared minus 24 equals 0. If I rearrange it, I get 3x squared, it's 12. I get x is plus minus 2. So here I get the points x is minus 2, y is 2, or if x is 2, y is 2. So we see that for this function of two variables, there are 4 critical points. So there are 4 critical points. And so now we need to classify these 4 critical points. So this function had 4 critical points. So we're not drawing the surface. We are going to use theorem 1 points. Now again, we're going to use theorem 115 like we did in question 4. So let's start off by calculating the second. So this second order partial is to the calculation. We get 6y minus 12, and this is continuous on R2. If we calculate this second order partial, it works out to be 6y minus 12 again, and this is continuous on R2. And if we calculate the next order partial, which is xy, this works out to be 6y, and this is continuous on R2. And we see all second order partials are continuous on R2. So we can use theorem 10. So we can use theorem 115. All right. So theorem 115 does have conditions, and the conditions is that f has to have continuous second order partials and an open set. And R2 is an open set, so we can use theorem 115. All right, and now we get to do the fun part. Now we classify the points. Let's start with the origin. So if I calculate d at origin, that is going to be f double x at the origin times f double y at the origin minus the mixed order partial at the origin squared. So if I plug in the origin, I get minus 12. If I plug in the origin into that, I get minus 12. And if I plug in the origin, I get naught squared. And this calculation works out to be the value 144. And 144 is positive. So let's say that 144 is positive. Now we know from the previous question we need more information. So f double x at the origin works out to be the value minus 12, which is negative. So origin is a local maximum. Great. So if we know that if the f value is negative, it is a local maximum. All right. Now, if it's a local, sorry, if this is if maximum, then I made a tiny mistake over here. So let me just scroll back. So here the classification should be this is a local maximum because d was positive and d double x is negative. So this is also a local maximum. All right, and this is what happened for this question at the origin. So at the origin, we see that D is positive and F double X is negative, so it is a local maximum. Now let's have a look at the critical point, which was 0, 4. So D at this critical point, I'm going to leave it for you to do the calculation and see if you agree with me. I got the value of 144, which is positive. And so now, again, if D is positive, we need more data. F double X at the critical point 0, 4 works out to be the value 12, which is positive. And if F double X is positive and if D is positive, we can now say that the point 0, 4 is a local minimum. Great. So we've classified those two critical points, but we're not done yet. We also have to look at critical point 2, 2. So D at the point 2, 2. Again, I'm going to leave it for you to see if you agree with my numerical value. This time around, I got 144. This is negative, right? So tell the marker that D at the point minus 144 is negative. And do you remember what it means if D is negative? Yes, it means that it is yes, you're quite right, it is a saddle point. So D is negative, so we don't need more time to say so. Point is a saddle point. We have one more to do, and it is the critical point 2 minus. Again, I'm going to leave it for you to verify that if you calculate D at the point minus 2 minus 2, I got the value of minus 144. Important note here is that that value is negative. So the critical point 2 minus 2 is a saddle point. And that, ladies and gentlemen, is the end of this question and is also the end of this worksheet. I hope you enjoyed listening to the answers of worksheet 8. Till next time, have a good day.